Hi class! In this lecture, I would like to talk about the basic physical solutions and extreme points. Keys of this lesson include to know the definitions of feasible solutions and to know the concepts of the extreme point being a basic feasible solution. Before we continue, we need some assumptions for group proof. To avoid certain technical complications, we assume that there are no redundant constraints in linear program and that the solutions are not encountered degenerate. Not degenerate, which means no cycle in simplex algorithm. First, we need to know the concepts of convex set. What is convex? A subset of S of Rm is convex if for any 2 points, x and y in the X, the line between x and y is given z equals to t times x plus 1 minus t times y, and this t, the value is between 0 and 1. This z is also belong to x. And also we said that the z is the combinations of x and y and fulfill with this equation. If there are only 2 variables, x and y, and x is x1 and x2, y is y1 and y2. In 2-dimensional graph, we can represent z by x and y. The first one we consider z1. And we can use the proportional relationship between xy and yz. So we use the z1 and y1, okay? And the z1 minus y1 divided by t equals to x1 minus y1 by 1, okay? So we use this line segment and this line segment proportion relationship, and then we can get the z1 is equal t times x1 plus 1 minus t times y1. Also, we can use this concept to get the z2, right? I think it's the same. You can use this one. Proportion to this one is t and 1. Okay? And you got the relationship between the x2, y2, and z2. So finally, we combine x and y and get this relationship. Okay, so here there are 2 sets. The first one is this square. Okay, and we give arbitrary line segment. For example, here is x, here is y, okay, and this is the segment of the line, okay, and we'll see any 2 points connect together still within this set, right? But if you consider like this one, we have here, maybe here is x, here is y, then you will find the segment here is not in the set of x. So for this one, we'll say it is a convex set. But for this one, is not convex set. Okay, So it's very easy to do the judgment by the graph. And because the x and y, we say that our feasible solutions belong to the convex set, and the z is the combination of x and y. So we will know any z in this line segment also the feasible solution in the convex set. Now we talk about what is the extreme point. So the definition of extreme point is an extreme point of a convex set S is a point S such that if X is expressed as a convex combination of 2 points Y and Z of X. Okay, so we say that if X equals to T times Y and plus 1 minus T times Z, and also Y equals to Z. So what will happen? So X equals to Y, Y equals to Z. So the final result is between X and Y and Z. There is no difference, only 1 point. So what is the extreme point? So extreme point of a convex set is only one which does not lie in the interior of any line segment of the set. Okay, so if you consider the linear program of only 2 variables, you will see this one, this one, this one, and this one, and this one, right? They are only 1 point in the convex set. And according to the problem, we have the optimal solution in the extreme point, right? And also all of the extreme points are basic feasible solution. So in 2-dimensional graph, we can use the graph represent the feasible basic solution. But what about more than 2 variables? Can you still use the graphical representation to represent endpoint? It is very difficult, right? Maybe in 3-dimensional, you still can use the cubic to represent the extreme point. But if more than 4, it is impossible. So we need to use some mathematical relationship and try to define the endpoint and the feasible basic solution. Okay, so now we'll try to use the matrix representation to represent the basic solution as a linear independent set of the vector. So now we'll give the more detail about the terminology of the solution. The first one is the basic solution. To a problem, what is the basic solution? Is we try to edit select variables added into the original constraint and setting all but one variable for each constraint equal to 0 and then solving the resulting system. So the solution we will call it basic solution. So what is the basic feasible solution? Which is also a basic solution, but all coordinates are non-negative and all constraints are satisfied. So in basic solution, there might be some points are not in the feasible region. So what is the optimal solution? It is a basic feasible solution which optimizes the objective function. And what is the basis? So basis is the set of variables allowed to be non-zero in a basic solution. Okay. And in order to do the proof, we need some basic knowledge of linear algebra. And if you have no background of linear algebra, I think it is better for you to find a book to do some basic study about the linear algebra. Like what is the linear combination of the vector and how define a matrix and so on. Okay, so now I just very briefly talk about the basic knowledge of linear algebra. So first one, what is the system of equation? We use the ax equals to b. If this system of equation has a unique solution, if and only if b is the linear combination of columns of A and column of A form the linear independent set, which means you have independent basis vectors and combine and form a solution to fulfill the ax equals to b. So what is the linear dependent? Okay, so if you have a linear independent basis, you just reduce one and eliminate one of the vector, then it will form a linear dependent vector. And for square matrix A, it has an inverse if and only if the columns of A forming a linear independent set. So the concept of linear dependent or linear independent are very important for linear program. So I suggest you, if you are not familiar with the knowledge, maybe you need to study more, because in this course we are not cover not all of the linear algebra in this course. Okay. So now we have LP models. Okay, and we will do some modification in order to do the proof. We assuming that we added the select variable into an n variable and the n constraint problem of LP, and all of the inequality becomes inequality. Okay, so here original is a x less or equal than b, then we added slack into that, but we are not use the symbol for s1, s2 and so on, okay, to sn. We use x n plus 1 to x n plus m in order to do the proof. Okay, so now we try to use the system of equation to get the basic solutions and to explain why extreme points will be the basic feasible solution for the problem. Okay, so now we assume that the x vector is the feasible solution for the LP models, and the extreme points of the set is the feasible solution if all the xj is larger than 0, forming a linear independent set is what we want to prove. Okay, so now we try to start our proof. So we will re-indexing the column and variables, and if necessary, we assume that only the first R components of X are positive. So with here x1 larger than 0, x2 larger than 0, here xr larger than 0, others x are equals to 0. Okay? So what we need to show the proof is that x is extreme point, if and only if. Okay? The corresponding set column A1 to AR is linear independent. So this is our purpose to do the proof. Okay, so the concept is we try to use the contradiction to do the proof. Okay, so we do the only if. Okay, so the first part of proof is we assume that the columns is not linear independent, because we try to do by contradiction. If we assume that all of the columns is not linear independent, and we will find something wrong in this proof. So the opposite side is correct, which means the set of columns are linear independent. Okay, so according to the definition of linear independent, is this one. Okay, if all of the C1 to CR equals to 0, then we say that A1, A2 till AR are linear independent. But now, because they are not linear independent, so definitely there exists at least one J not equal to 0, and fulfill with this equation. Okay, so we will assume that the C equal to C1 to CR, this one is 0. Okay, so this is the assumption. Okay, maybe you will say that why we need to assume that C1 to CR are not equal to 0, others to 0. Okay, this is just one case because we need to do the proof. You might be assume others vector, but it will be very difficult. This way is the simple way to do the proof. Okay, any case of the assumption are okay. Then, according to the assumption, we can rewrite. Okay, the vector A times vector C equals to 0. Okay, and then now we only consider two variables. Okay, you might be said if two variables, okay, maybe we need to use 3 variables, 4 variables. Do we need to do the proof for 3 or 4 or 5 variables? The answer is no. Why is that? Because now we use the contradiction proof. We only need to find one case to violate our assumption. Then we can prove our argument. Okay, so we assume that W is equal to X plus lambda times C, and W bar is equals to X minus lambda times C. Okay, and the condition of lambda is small enough so that lambda times C is less than Xj, and J from 1 to R. Okay, if we have the condition of this one, we can guarantee that W is larger than 0 and the W bar is larger than 0, right? Because you can put here, okay, this one is larger than 0 and this one is larger than 0, and this one, because the Xj is larger than lambda times c, right? So this one is also positive. Okay, so we can put the w and w bar into the ax equals to b, okay, to verify if w and the w bar are feasible solution for the systems of equations. Okay, so we put w into the ax. Okay, so here is ax times lambda ac, and because ac is 0, right? AC is 0, right? So here AW equals to AX and AX equals to B, right? And here is the same. Here is the same. AW bar is equal to the same. So we know if the X is the feasible solution for the system of equation, then the W and the W bar are also the solution for the system of equation. And then we try to use the relationship. Okay, so we say that we can times W for 1/2 plus W bar 1/2. Okay, then you will see W, okay, so W and W bar do the linear combination for X. That means X is between W and W bar. Okay, so because we know that X is the extreme point, right? So which means it will not the same as W and the W bar. Okay, it only have one point, which means X should be equal to W and W bar, like this one, right? Which is the contradiction, right? This is the result. Okay, this is the actual. So if we assume that the A here, okay, is not linear independent, okay, it should be linear independent, but according to this result, we have a contradiction, which is not extreme point. There are line segment. Okay, so we find it should be A is linear independent vectors for X. Okay, and then now we need to do the proof for if. Okay, so now we assume that A1, A2 to AR is linear independent set, and also we assume that X equals to the linear combination for Y and Z. Okay, and in before we already said that if X is an extreme point, then it should be show that X equals to Y equals to Z. Okay, how can we do that? We just do some assumption. Okay, so now J is from the 1 tier n plus m, and all of the Xj is fulfill the same relationship from Y and Z. Okay, so because Y and Z now are the feasible solution, then we put all the Y into the system of equation and the Z put into the system of equation. Okay, and finally we'll see Okay, and put all into it, and we combine all of this together. Okay, all of this together, and this one, these two. From the left hand side of the equation, which means here is x, right? Okay, because when you put all things into it and you have a relationship put into it, and you will find here is like this. Okay, so what is this? It is ax, right? And what is right hand side? Okay, you put all in here. You will find this one is here, right? So it will become ax equals to b. So you will know actually y equals to z equal to x. Definitely x is a feasible solution. Okay, so you put all of the relationship here, right? And you got all of the x, y, z equals to a inverse b, right? So you will know all of the x and y and z are extreme points because they are the same. Okay, so all of this one explains if you have an extreme point, then it will be the feasible solution for your system. That means all of the feasible solution will locate it to the extreme point of the feasible region. So optimum definitely will one of these feasible basic solution. Okay. So I think the proof is a little bit difficult for you because you need some background of linear algebra. But I think you need to know a little bit more, like what is the definition of linear combination, what is linear independent or linear dependent. If you know the definition of this and know some basic operations of the matrix, then you will feel comfortable about this proof. Okay, this is the lecture what I want to talk about. See you in the next lecture. Bye bye.